Alright, hello students. Welcome back to another video for ComSci 137 Data Communications and Networking. Before we continue, let's have a short review of last video's topics. We talked about data and signals, and we talked about digital data and analog data, and then we also talked about periodic analog signals. So in this video we'll focus on digital signals. So what are digital signals? So remember that if we have an analog data or a digital data, we need to convert them to either analog signal. So this is data, this is signal. We need to convert them to signals, because the signals are the form, or is the form that the transmission can carry across the transmission medium. So recall that if we have a communication link here and we have another party here, so we have A and B. Let's say we have voice here, voice. If we have a voice, that is an analog signal, and if we want to transmit it across this link, we can use a analog signal, or we can use a digital signal. If we use an analog signal, that will be the telephone system or public plain old telephone system, and for digital, this can be, say, voice over IP, right? So if you want to send a picture, on the other hand, this is a picture, then this is digital data. We can also use analog or digital signals to transmit them across the medium, because by itself the data cannot directly be transmitted across this link unless they are converted into a transmittable form, which is basically the notion of signals. So we discussed periodic analog signals last time, and basically we said that analog signals are represented by sine waves, and if we have what we call composite signals, which are composed of simpler sine waves, which are basically harmonics of the main frequency or the fundamental frequency. So we now focus on digital signals. So the idea here is a 1, as in the case of a picture here, can be encoded as a positive voltage. This is a positive voltage, and a 0 can be encoded as a negative voltage. A digital signal can have more than 2 levels, and if you only have 2 levels, positive and negative, then we can send only 1 bit per signal, because this one will represent 1, 0, 1 0 1 0, etc. In general, if a signal has L levels, each level needs log to the base 2 of L bits. So that means it can represent log L to the base 2 bits. So what do we mean by that? So this illustration explains that further. So considering this scenario, this figure, on the y-axis we have the amplitude, and the amplitude there are two levels, level 1 and level 2 and level 1. And the y-axis, the x-axis is time. So normally digital signals are not periodic or aperiodic and periodic. So in this scenario, within 1 second, 1 2 3 4 5 6 7 8 bits are sent in 1 second. This means that the bit rate is 8 bits per second. So notice that we're using the bit rate value here. Now if we have this example 4 levels, so we have level 1, level 2, level 3, level 4, which can represent voltage levels, for example. Then in a given second, if we have 4 levels, we can map, let's say level 0 will be level 4 will be mapped to 1 1. Level 3 will be interpreted at the receiver end as 1 0. Level 2 will be interpreted as 0 1 at the receiver end, and level 1 will be interpreted as 0 1. And level 1 will be interpreted as 0 0. So the drawing shows that this is the same. So this is 0 1 0 1. So that means level 2. And as you can see, in a given second, we were able to send 16 bits. 1 2 4 2 times 8. That's 16 bits. So as a result, the bit rate is 16 bits per second. So that means that indeed by increasing the number of levels, we can increase the bit rate. That's an important property of digital signals, because we can increase actually the number of levels so that we can increase the bit rate. So unlike in the analog signal, in digital signals, in the analog signal we use frequency, amplitude, and period to describe the signal. In digital signal we use the bit rate, because most of digital signals are non-periodic, so the frequency and the period are not appropriate descriptors. And based on the previous illustration, the bit rate is the number of bits sent in 1 second expressed as bits per second. So you'll be able to see that here. Okay, so this is the number of bits sent per second. We also define bit length. In the analog signal, we have wavelength. You can recall the formula in the previous video. In digital signal, bit length is the distance 1 bit occupies on the transmission medium. Okay, so transmission medium. Okay. It's the distance. Okay. Let's say we have bit 1. What is this distance? That is the bit length, and the formula to compute the bit length is propagation speed multiplied by bit duration. Okay, so that's an important property to remember. Okay, so in the previous video, we talked about signals being composed of simpler sine waves. That's also true for digital signals. So the figure here shows two digital signals. On the left, we have the time domain of this digital signal. So two levels, level 1 or level 2, and then level 1. And then if we get the frequency plot of this digital signal, this is what we're going to get. So we have a fundamental frequency, harmonics of the fundamental frequency, and it's basically infinite. You see, it has infinite bandwidth, and this is a periodic digital signal, but most digital signals are aperiodic, as shown here. Okay. So normally you don't send a pattern of 1 0 1 0 1 0 1 0. So usually it's non-periodic, and like this one, this is a single bit. So if we plot the frequency domain of this digital signal, this is what we're going to get. So it's also an infinite bandwidth, but you have continuous range of frequencies. Unlike here, you have discrete frequencies because you have because this signal is periodic. Okay, so it's important that you understand the most modern data communications use digital signaling, and it's important to understand first that digital signals are non-periodic, and the frequency plot is a continuous plot, but still also infinite. Okay. So next is, how do we transmit digital signals? Okay. So how can we send a digital signal from point A to point B? Data communications use non-periodic digital signal. It has infinite bandwidth, as shown in the previous figure, and a continuous range of frequencies. Now, there are two ways to transmit a digital signal. The first one is called the baseband, and the second one is called broadband. So probably the word broadband is familiar to you already. But let's see what this means in terms of digital transmission. So in baseband transmission, you sends a signal, digital signal, without changing it to analog signal. So it is as is. What is the main requirement? It requires a low pass channel, a channel with a bandwidth that starts from 0. Recall our discussion about bandwidth. Okay. And there are two approaches for this. We have a low pass. If you are given a low pass channel, that means a channel with a bandwidth that starts from 0 and a wide bandwidth, then the shape of the original signal will be preserved. Whereas if you have a low pass channel but with limited bandwidth, we can approximate the digital signal with an analog signal. So you have to recall the definition of bandwidth, right? If we're going to consider this, the bandwidth is actually from here to here. But since this is a digital non-periodic signal, this is actually, the bandwidth is actually infinite. So this is some illustration of a low pass channel with a wide bandwidth. Example used in local area networks. The cables used in local area networks like the UTP, the coax, and the fiber optic. These are examples of transmission media with low pass channel and wide bandwidth. So let's say we have this input signal. So again, this is a digital signal which is non-periodic, and if we plot the frequency domain, frequency plot, we get this 0 to infinity. Okay. This is the shaded area. Then this is the wide bandwidth channel. So you have F1 here, which may be 0, then F2 here, and then we pass the signal here, and then at the receiver end, the output signal somehow resembles the original signal. So that's the advantage of having a low pass channel with a wide bandwidth. Thus the second alternative is, what if you don't have a high bandwidth channel? So you have low bandwidth. So you have to consider the worst case scenario, which is basically alternating ones and zeros, 1 0 1 0 1 0 1 0 1 0. Okay. So let's have an example for 3 bits. So you'd like to send 3 bits. So this is this will be the plot. Okay. So the idea is to approximate the digital signal with the corresponding analog signal by using different properties of the analog signal. For example, to represent 0 0 0, which is this digital signal, we can use an analog signal with a frequency of 0 and a phase angle of 180 degrees, which will look like this. So notice that there's no the frequency is 0, no change in the waveform. And to represent 0 0 1, we can use this analog signal frequency n over 4. So take note that this is the bandwidth. Okay. and this will be the appearance of the equivalent analog signal for this digital signal. And then for 010, this is the waveform for the digital signal. This is the approximation. This is the approximate analog signal that will be transmitted to the channel. So at the receiver end, when the receiver receives this waveform, it will be interpreted as 010. So that's what we mean by this example. So we are given this input and we were able to generate this plot, frequency plot. So in this illustration, we simply use a few frequency components for the signal. That's why the approximation is not quite good. But if we increase the bandwidth, so in essence, if we increase the number of frequency components to represent the signal, in this case we only use n/2 for the bandwidth, but here if we use this bandwidth 5n/2, then the approximation will actually be better. Right? So as you, for example here, f is n. This is the just one frequency component, f equals n/2. So this is the plot. Although it looks like the digital signal, but it's not that square. But if we use two frequency components, f equals n/2 and component 3n/2, then we get this approximation. And if we add more components, you will see that the analog signal realistically approximates the digital signal. So that means that in order to really accurately represent the digital signal, we can add more frequency components so that we get a better approximation of the digital signal. So some problem solving schemes here. Some problem. Question is, what is the minimum required bandwidth of a low pass channel if we need to send 1 Mbps using baseband transmission? So first, the bandwidth is actually, or the bandwidth is actually equal to the bit rate divided by 2. Okay, so we have 1 Mbps divided 1000 bps divided by 2. That will give us a minimum bandwidth of 500 kilohertz. So another problem is, what if we have a low pass channel with a bandwidth of 100 kilohertz? What is the maximum bit rate of the channel? So bit rate is equal to 2 times the bandwidth, which is 200 kbps. Okay, so notice the difference here, the unit. First, when we talk about the bandwidth, our unit is hertz. But when we talk about bit rate, our unit is bits per second, and the formula is the bit rate is actually twice the bandwidth. It's the ideal. Okay, so we're done with the baseband transmission. So the next one is broadband transmission. So here, the idea of broadband is it changes the digital signal to analog signal for transmission. Okay, so unlike in the baseband transmission, the digital signal is not changed. In broadband, there is a conversion. By doing this, it allows the use of a band pass channel. Okay? And unlike in the baseband transmission, wherein you have a low pass channel, in the broadband transmission, the band pass channel is a channel with a bandwidth that does not start from zero. Okay, because there are some transmission media that does not, with a bandwidth that does not start from zero. So you need to adjust the signal, translate it actually. An example will be the DSL, direct subscriber line, and cellular networks. So what happens in a broadband transmission? So we have this input digital signal, and then this digital signal will be passed to a digital to analog converter, and then it will output an analog signal within this band pass channel with this bandwidth. So this will be an analog signal. Notice that is now sine wave. Then if we have this band pass channel, it has this bandwidth. So after changing, this analog signal will now travel to the transmission media. Then at the receiver end, it will receive an input analog signal, and this is the property, the bandwidth of that signal. And then it will pass to the modem. So this will be analog to digital converter, and then you get back the original digital signal. So it's actually called a modem. But during the early days, when we want to connect to the internet, our homes, in our homes we have the telephone, for example. So what we're going to do is to remove the connection from the telephone landline, then connect the telephone, the cable to the modem, and then you run a dial-up program from your computer, and then you will get connected. So normally we buy internet cards before with the corresponding pins that allows us to connect to the internet. So that's an example of broadband transmission. The same with cable internet, for example. So I'm using QuickNet, and my connection is passing through the cable, coax cable. So it's also possible using a broadband transmission. So I guess those that covers the transmission of digital signals. So to summarize, we have baseband and broadband, and the main difference is in the baseband, the bandwidth has a frequency that starts with 0, whereas in the broadband it can be anywhere. Okay, so during transmission, it's not always the case that the transmission will happen smoothly. So in the same way that we communicate, let's say if I'm delivering a lecture and somebody is noisy, then other students will not be able to hear my lecture. So in digital communications, we also have transmission impairments. And there are several types of transmission impairments. And let's start with attenuation. So attenuation, it is natural that the energy of a signal decreases as it travels through a medium. For example, when you're talking to someone from a distance, if the other person is too far from you, he will not be able to hear you, because let's say your voice has only a limited range, and that's because of attenuation. Now in data communications, if you want to increase the signal, the energy of the signal, you use amplifiers to do that. For example, you can use a megaphone. The megaphone is an amplifier. So if you have a soft voice, you use a megaphone to enhance your voice. So it amplifies your voice. And the unit of measure for attenuation is decibels, dB. So perhaps if you see this in sound systems, it measures the relative strengths of two signals, or one signal at two different points, and the formula is this one. So P and R, these are power levels. Power levels at, say this is your party. So you measure your signal at this point, the signal, then you measure the signal at this point, then you plug that in and you get the attenuation. So here's an example. You have point 1, this original signal. So as the signal propagates across the medium, you will notice that the peak here is smaller. So at this point 2, there is attenuation. Now if we use the amplifier to boost the strength of the signal, we get the original signal back again. So that's the purpose of the amplifier. So here are some computations associated with attenuation. What is the attenuation or power loss if a signal loses power by 1/2 when it travels through a wire? So if we let the original power to be P1, then it loses by 1/2, so that is 0.5 of P1, then we get -3 decibels. Negative means attenuation. Now a signal, another computation, another problem, a signal is amplified 10 times. What is the amplification or the power gain? So we actually You see this when you record. I use this when I record my video. So usually my microphone will capture a very low sound. So I can increase the gain so that the volume will increase. Basically by specifying decibel levels. So going back to the problem, this is the original power level. It is amplified and becomes 10 times than the original, and we get 10 dB. So that's essentially what you do. If you're using OBS and when you listen to your recording and the sound is too low, you can increase the gain, basically amplifying the strength or increasing the volume. Okay, so here's another example without the solution, so it will be left for you to solve this. So a signal with a starting power of 2 milliwatts travels on a cable with this attenuation. What's the power at 5 kilometers? So essentially you're looking for the value of P2. What is P2? So you simply have to manipulate the parameter here. Okay, the second transmission impairment is called distortion. So the signal changes its form or shape. Remember that a signal is, most signals are composite signals, meaning they have different components sine waves, and these component sine waves can travel at different speeds, and thus they may be out of phase as they travel through the medium or through the channel. For example, we have this composite signal. When it travels to the channel or transmission medium, it will travel using the different component sine waves. Remember that using Fourier analysis, this composite signal is composed of different component sine waves. When these travel at the receiver end, they may be out of phase because they have different characteristics as they travel through the medium, and at the receiver end there might be some distortions. So the original signal is no longer the same as the received signal. So that's distortion. If you are in a band, so you have a device, a distortion, so you can change the sound of your guitar or something. So that is distortion. So the third transmission impairment is noise. So noise, probably you know this already. There are 4 types of noise. We have thermal, induced, crosstalk, and impulse. When we say thermal, it comes from the random motion of electrons. So recall that some equipment becomes hot when it's continuously running because of conduction happens because of electrons, and because of resistance then heat is produced, and this heat affects the signal as the signal travels through the medium. Then we have induced external sources. For example, some Some devices acts like antenna, and they affect or generate signals that they affect the signal traveling on a link. Example, refrigerators or ovens or other home appliances that are electric appliances. They sometimes produce signals that can affect the signals traveling on communication link. Next is crosstalk, wherein one wire is touches another, so that's called crosstalk. That's why sometimes when you use the landline, you hear different conversations or you hear other conversations. That's called crosstalk. And then impulse noise. So for example, there is the lightning, and of course the lightning will generate some electrical signals, and that will also affect the transmission. So that's those are the three main transmission impairments. So normally to measure noise, we have a metric called SNR, signal to noise ratio, which is the average signal power, and then divided by the average noise power. And you can use the decibels unit also for representing signal to noise ratio, which is this formula. So SNR is this one. So this is an example of a noise. So this is the original signal, and then suddenly there is a lightning, and then the signal is affected, and then at the receiver end you will see the fluctuation being incorporated in the received signal. So that's why when there is a thunderstorm, usually you are asked to switch off your devices, electronic devices, because the signals will be affected. So that's a sample of impulse noise. Okay, so we now know the different characteristics of data signals and transmission impairments. Now, is there a limit on the data rate? So data rate, as I've said before, is really related to bit rate, number of bits that you can send per second. So it's bps. Now the data rate depends on the bandwidth, the available bandwidth, and also on the level of the signals we use and the quality of the channel. So these are the considerations when we are talking about the data rate. In the previous computation, if you are given a bandwidth B, then we multiply that by 2 to get the bit rate. So essentially these are directly proportional. Levels of signals we use, remember that we can represent log 2L, which is the number of levels. So the bigger the L, the larger the number of bits that we can use, or the more number of bits can be used to represent a single signal, as we've shown earlier. And of course, the quality of the channel. For example, if the channel is a fiber optic cable with very low attenuation, then the signal, the intensity of the signal will not be affected, and there will be no errors when it comes to the interpretation at the receiver end. Now, there are two limits, or theoretical limits when it comes to data rate. The first one is the Nyquist bitrate, which is for noiseless channel, and then we have the Shannon capacity, which is for noisy channel. So in the Nyquist bitrate, okay, so the unit is bits per second, and L is the number of signal levels. Then the maximum is twice times the bandwidth, shown here, multiplied by this one. So that is the theoretical limit, assuming that we have a noiseless channel, say in space or in a vacuum. For the noisy channel, the limit is given by the bandwidth and the signal to noise ratio. So notice that the Shannon capacity does not include the number of levels, number of signal levels. It's just the bandwidth, which is the same as the Nyquist, and signal to noise ratio, which we defined here, the average signal power divided by the noise power, because we are considering a noisy channel. Okay, so the problem with increasing the number of levels is that it's difficult for the receiver to interpret the different levels. Unlike if you have a binary only, you have ones and zero, high or low. It's very easy for the receiver to interpret. So as the number of levels increases, the reliability decreases. Okay, so these are theoretical limits, and usually the actual data rate that is obtained is less than these theoretical limits. So the Shannon's capacity gives the upper limit, and the Nyquist formula tells how many signal levels are needed to achieve that particular bit rate. Okay. So you can actually integrate both of these limits in solving certain problems. For example, you might be asked, given a bandwidth and an SNR for a channel, what are the appropriate bitrate and signal levels? Okay. So That's an interesting problem. Okay, so just have an example. Okay, we have an example here. What is the maximum bitrate of a noiseless channel? So there is a noiseless channel. If it's noiseless, we use the Nyquist theorem or Nyquist limit, and we have a bandwidth of 3 kilohertz transmitting at 2 signal levels. So we are given all the information. We have the bandwidth, which is 3 kilohertz, and 2 signal levels, and the bit rate that we're going to get is 6,000 bits per second or 6 kbps. Second problem, how many signal levels are needed to send at 265 kbps over a noiseless channel with a bandwidth of 20 kilohertz? So we are asked to find the value of L. So by plugging in the given values, we're going to get this number of levels. So given these characteristics, we need 98.7 levels to achieve this. That is quite large, and it will be very difficult for the receiver to distinguish these different levels. Another example, we have a telephone line that has a typical bandwidth of 3000 hertz, so from 300 to 3300 hertz for data communications, and as an SNR of 3162. What is the capacity? So the capacity is the bandwidth, which is 3 hertz, log plus 1 plus the SNR, and solving for this we get 34 kbps, which is the standard for dial-up connection. Or 34 kbps. Okay. So those are some computations related to the data rate limits. Let's talk about performance. So in data communications, we are interested about performance, and we have different metrics to measure the performance. Of course, we know bandwidth, and there are two ways to interpret bandwidth. It can be interpreted in terms of the hertz, so using the hertz unit, or for analog or digital signals in bits per second. Hertz is useful for periodic analog signals. Examples, in the telephone system, we have a 4 kilohertz bandwidth, which enables the voice communication, and 56 kbps for data communications. So normally these bandwidth are just theoretical values. The actual data that is actually sent across the network is called the throughput. Okay? So how fast we can actually send data to a network. So it's always less than the bandwidth or the data rate. And the main reason is devices may not be able to handle a high bandwidth. For example, you have a switch here, a device, and this is 1 Gbps. And if you have a computer here, with only 100 Mbps. Right? Even though you say that you have a connection of 1 Gbps, if your device can only process 100 Mbps, even though you have a 1 Gbps connection, you'll only get a maximum of 100 Mbps because the device cannot handle high bandwidth. Okay? So you have to buy a LAN card that supports 1 Gbps. Okay? So that's a tip when you buy your equipment. Make sure that your equipment can support the data rate provided by your ISP. Let's say you just buy a router from Lazada and then you have a Gbps connection, but your router from Lazada can only support 100 Mbps, then you really will not be able to take advantage of the Gbps provided by your ISP or fiber, whatever connection you have. Then the third metric for performance is called latency or delay. It describes how long it takes for an entire message to completely arrive at the destination, starting with the first beat. For example, you're going to send your picture to your girlfriend or your boyfriend. Now, a picture has certain size, file size, and it's composed of bits and bytes. If you send that across the network, what you can compute the delay for that, or the latency, and we have a formula for the delay. Delay is affected by several parameters. The first one is called the propagation time. The second one is the transmission time. Third is the queuing time, and then fourth, the processing delay. So when you talk about latency, you have to consider four factors. These four factors. So going back, so this is for the delay. Okay. So propagation time is the time required for a bit to travel from source to destination. So let's say you have your picture here. So you have the first bit of the picture to be sent across the network. How long does it take for this bit to go from A to B? That's called the propagation time. And the formula is the distance and the propagation speed. So this is usually speed of light. So that's propagation time, and this is the formula. For the transmission time is the time to transmit all the bits. So how long does it take? So this is your picture. It's composed of several bits. How long does it take to transmit, right, all the bits of this picture to the link? So that's transmission time. It's actually the formula is the message size divided by the bandwidth. So remember that the channel or the transmission medium here has bandwidth property. Then the third one is queuing time, which is the time to hold the message before it is processed. So normally, if you have an internetwork, you have intermediate nodes so that data will still be stored there temporarily. So let's say if you have a router here, your picture will be stored here temporarily while waiting for routing decisions. So that is queuing time. And the last one is nodal processing. So the task being done here. So here is the illustration. So this propagation time, transmission time, queuing delay, and nodal processing. Those four factors affect the latency or the delays in packet switch networks. Examples, what are the propagation time and the transmission time for a 2.5 kilobyte email if the bandwidth is 1 Gbps. Assume the distance between the sender and the receiver is 12,000 kilometers and light travels at 2.4 times 10 to the 8 meter per second. So we can compute the propagation time. So the propagation time is the distance divided by the propagation speed. So the distance is 12,000 kilometers. So we have to convert this to meters. So multiply by 1,000. And then the propagation speed of light. So the propagation time is 50 milliseconds. Now the transmission time is message over the bandwidth. Okay, so the formula here, the message size divided by the bandwidth. So we have, since this is 2.5 kilobyte, so 2,500 multiplied by 8, because 1 byte is 8 bits. And then the bandwidth is, notice that the bandwidth is in bits per second, so we have to convert this to bits. So 10 to the 9, and we get the transmission time of 0.020 milliseconds. Okay, so we also have another measure called the bandwidth delay product, which defines the number of bits that can fill the link. Okay. The idea of bandwidth delay product is, normally you have a channel or a transmission medium with a high bandwidth. Okay. And the bandwidth delay product will allow you to make efficient use of that link with high bandwidth. So let's take the first figure. So in this illustration, we have a bandwidth of 1 bit per second and a delay of 5 seconds. Okay. So this is the sequence of bits that will be on the link. Okay. So the first bit after 1 second is here, then this first bit will, after second 2, time 2, it will be at this point, and so on and so forth. Okay. So only 1 bit can fill the link. Okay. But here, if you have a bigger bandwidth delay product, okay, you can, in 1 second, you can send the first 5 bits, and then the second 5 bits, the third 5 bits. So 1, 2, 3, 4, 5. If you have this bandwidth delay product 20 bits, meaning in 5 seconds you have 20 bits that are flowing across the link. Whereas if you have a bandwidth delay product of 5 bits, then in 5 seconds you can only, the wire or the link has only 5 bits in it. Okay, so that's the main idea about the bandwidth delay product. So because we want to make efficient use of the transmission link. So this is important when we go to the data link layer, when we talk about flow control. Okay, so in the idea of flow control, we should make sure that there are bits traveling on the link, present on the link. We will discuss more of this later, but flow control is very important to make efficient utilization of a link. Now, this is just the formula, so it just defines the number of bits that can fill the link. So here you can have 5 bits, here you have 20 bits. Okay, the last one is jitter. So jitter is for time sensitive data like audio and video. So it also an issue when it comes to the performance of data communication networks. So you don't want jitter in your live stream, okay? You don't want jitter in your video conferencing or in your streaming. So there are different techniques for solving jitter in communication networks. Okay, so I guess that ends this chapter, and I hope we've achieved the objectives for this chapter 3, which is all about signals, data, performance metrics. Stop here and see you on the next video.